Hi guys, can I get a sound check?
Sounds good.
Okay, thanks, Elvis. What am I doing? Man, I'm impressing myself. I managed to make it to class 2 days and 2 lectures in a row. Small steps. All right.
Professor, I don't think we can see you.
Oh no? Well, that's a mixed blessing, Amy. Let's see. What is going on? Huh. I got my video on. Oh, maybe it's looking at a different video. FaceTime, no? FaceTime. Ah, there we go. Now you should see a very fuzzy picture, which is a complete embarrassment for somebody who spent his whole life building image sensors and camera systems. But I'm doing something about it. Okay. Are you guys, how is my internet connection okay? I think my internet connection may not be so great. Are you guys hear me okay and everything? Okay.
Yeah, we can hear you fine.
Okay, great. If it goes down, I'll just log back in. Start broadcast. Okay, guys, let's get started. So first administrative thing is I'm still struggling to come up with a date for the midterm. I'll ask for your forgiveness. I'll get something for you guys by Tuesday. Let's get my sort of think a little bit more about when to do the midterm. I'm going to take about another 5-10 minutes of your time. It won't be next week, no. So I'm not that mean. Is next week already? It's not 6th week, is it? Where are we? Time goes by.
Next week is the 5th week, I believe.
It's the 5th week. Jesus. Wow. Okay. Well. So it won't be next week. So probably at the very earliest it'll be in 2 weeks. So So you guys don't need to worry about next week. So let me just, I'm assuming that at least some of you are very confused about what we're doing in this class. So I wanted to take a moment and try to walk you guys through something that I personally find kind of like clarifies what we're trying to do in school, at work, you know, just as engineers, okay? And I hope it won't confuse you anymore. If I've talked to you guys about this already, I apologize, but I just love this concept. I think it really clarifies a lot. And it's, you know, the idea is the concept of layers of abstraction. You could think about it as design hierarchy. Kind of the same thing, more or less, okay? But this is the concept, and this is really important to us engineers. I don't know if other fields are like this, but for engineers, every aspect of engineering is, to me, is like this in some way. So let's take an area like computer systems that I'm sort of somewhat familiar with. Okay, so you have like a bunch of layers in a computer system. So it starts, you got at the very top, you've got your data. Okay, so that's the highest box. This is like a Word doc or an Excel doc or something like that, or a text file, something like that. Next level is an application. So like basically like Microsoft Word or Excel, something like that. Okay, excuse me guys, let me close my door because my dog's barking. Next level down is, you know, the API layer where you can have the different applications talk to each other. I don't know if you guys are familiar. I'm sure you're familiar with at least these two. API, I'm not sure about. Then you have the operating system. So that's, you know, Windows or Mac OS. And then the next layer is the processor. So anything above here is kind of more or less software. This is like firmware, but and here it's hardware. Then we got logic. Then we have sort of the physical layer. Then we have the device. And down here, we have physics, I guess, semiconductor, hard, whatever, solid state physics. Okay, so this is a computer system, and it's all the same thing. It's all the same thing. How you look at it has to do with which layer of abstraction you're working on here, right? If you were, say, an engineer working on like building, working on the operating system, let's say you're just a fully software engineer working on operating system, you are working, this operating system has to run on a microprocessor. It's actually running on a microprocessor, right? It's just meaningless to have this guy without the microprocessor. And the microprocessor is made out of logic elements that are doing binary math. Okay, AND gates, inverters, NOR gates, those kind of things. Those logic elements are made out of circuits. Okay, Then those circuits are made out of devices. Those devices are working on, principles of solid state physics. But if you were working on an operating system, let's say you're programming this thing, you're working on a Windows operating system. If every time you want to write a line of code, you were thinking about how a diode works, and we're gonna sort of we were gonna drill down all the way to every diode and transistor that was responsible for that particular line of code you would be writing, it would take you forever to get what you have done. So you can't do it like that. So when you have a complex system, what you do is at every level you're working in, you're kind of at a particular layer of abstraction. So for example, when you're doing programming, you're not really thinking about necessarily the particular registers on a processor or how exactly a memory, like a block level memory block works, a SRAM block, or how the hard disk is physically accessed. Okay, you're using a layer of abstraction for the processor. You kind of see it as a bunch of functional blocks that you have some register settings that you address, etc. That's how you look at it. So at each layer, because of the complexity of these systems, you're only looking up probably one layer above you in the level of abstraction and one level below you. But really, the actual system goes many levels down, many levels up, wherever you are. Okay, and so this is an example of a computer system, but a car would be the same. Let's say if you're working on the engine block for, I'm assuming like a gas engine, right? A car, I don't really know much about cars, but let's say we're working on an engine block for a car. You're not thinking about how, the oil viscosity is created and what chemical elements are used to create a particular viscosity oil. You're abstracting the concept of oil to something that's going in a particular container in the engine block, and it's keeping things running, let's say, in a particular way. So, I know Cal Poly, there's a lot of you guys that are probably there's a lot of work with like Edison and power delivery and generation, et cetera. I'm assuming I worked in that area, but if you look at your, electrical power going to a house, you can think of it all the way from electromagnetic fields and Maxwell's equations and those kind of things to the fuse box in your house. But if you're working on the fuse box, you're not thinking about Maxwell's equations or electromagnetic fields at that point, because you won't be able to deal with the problem at hand. Okay, so in this class, let me just first talk about your education, right? So your education as an undergraduate, you're kind of getting a flavor of each one of these things. Okay, and I think part of the idea is that in an undergrad environment, you need to know a little bit about everything, because when you graduate, let's say you have a problem with your processor, and you have to be able to debug that. You might have to talk to the people working on a device level to understand what the heck it is they're talking about, to be able to fix your own problem. Or if you're managing this whole enterprise, you better be able to talk to each one of these people and at least understand what they're up against and what language they're speaking. On top of that, you really don't know what area you guys are going to end up working in. Each one of you guys is going to have his own career or her own career. That'll be decided by a bunch of stuff like which one of these areas, for example, let's say we're going to go into computer systems, what you find appealing, or what internship you end up getting, or what first job you end up getting. So you get a little bit of everything. Okay, so that's the idea about these layers of abstraction. So in this class, we're working on sort of this layer of abstraction. So, we started by talking about devices, whether it's like a PN junction. So we talked about it a little bit, but we're mostly working here, which is at the level of circuits, basically. Okay, and in other classes, you'll move up to logic level, or maybe work on microprocessors or something like that. And in yet other classes, you might dig down deeper and talk about semiconductor physics or solid state physics in greater detail, right? But this is where we are, where we're talking about circuit elements like diodes, like bipolar transistors, MOS transistors, how to connect these up into simple circuits, etc. And again, we'll be talking a little bit about the devices and how these things, this level of abstraction below us. And then we might talk a little bit about a level of abstraction above us. As you go down in the level of abstraction, I find typically you're trying to create a more detailed and accurate picture. So you're getting a more complex model as you're working your way down, which is probably more accurate as to what it is that exists, right? I mean, there's no such thing, applications and stuff are just really sort of non-physical thing. They're just conceptual things, at least to me. But like a device, like a chip actually exists, the microprocessor actually exists, so on and so forth. But so as you go down in layers of abstraction, you're getting into more complex models, etc. What the majority of what we're doing in this class is we're starting with this sort of device level definitions, and we're going up in level of abstraction. So we're doing the opposite. We're creating a less complex model so we can build. So we're going up a layer of abstraction, and sort of by definition, we're trying to create more simplified models and analysis tools. Okay, so if you were working on a device level, so to bring it to today's lecture, right? If you're working on a device level, let's say at a company or something, you might work 6 months, a year on a diode. You might be optimizing that particular diode to have some particular characteristic, like in some way it's either like has lower resistance or higher power consumption, etc. So you're really digging into the details of that diode. If you're working on doing circuit design with that diode, you don't want to think about it at that level. You want to create a simpler model for the diode, because the diode is just going to be a piece in a circuit that you're designing, that there might be 50, 100 other things in your circuit, and this diode is just a piece of it, or this transistor is just a piece of it. So you want to create a simple model, as simple as you can get away with, but no simpler, as simple as you can get away with to do your design. And that's the discipline and techniques we're trying to learn in this class, is how to have, when can we use simple models for these devices? How can we use these devices with these simplified models in circuits that do something that we want? So it might seem that that's the direction we're going. We're not going in the direction of learning how the details of how a diode or a transistor works. I'm just giving you guys a real high level definition of it. And then I'm trying to jump into something that would help us design circuits with it, which means simplified models. And that's why, for example, we have 3 models of the diode. We have this exponential model, which as far as this class is concerned, so this VD, I sub D, is, the the device level model to some extent. So as I is equal to I sub s exponential of Vd over T minus 1. Okay, this model. And then we have more simplified models like so this is exponential model. So sometimes we have to use this model to do our designs. There's just no way around it. But if we use this model for every design we did, as you'll see, and you'll have to take my word for it now, you'd be really limited to how big of a circuit you could design, because it gets really complicated really fast. Okay, so we use a more simple model, which is the constant voltage model, which looks like this. So this is the constant voltage model, which is, a lot simpler to use once you guys get the hang of, you do a bunch of circuit analysis, doing the homeworks, etc. Once you get a hang of it, this is a lot simpler to use than this. There are some circumstances that you can't use this, which is very unfortunate. You have to go back to looking at it like this. Just like there's some circumstances where you can't even look at it like this, you have to go to actually think of it as a PN junction and a piece of semiconductor. I've had to do that. I sometimes have to do that for the stuff I do, but rarely. But we won't be doing that in this class. But I'm just saying, like, that's the idea, and that's why these different models exist. And as confusing as these models are and these different analysis techniques, the idea is that they are simpler analysis techniques or simpler models that allow us to go up a level of abstraction in how we do the design. So, and then finally we have this so-called ideal model of the diode. They're all the same, modeling the same diode, but again, as we work on the homeworks and so on, you'll see that this makes life a lot simpler in terms of analyzing the circuit, then does this, then does that. What else do I want to say here? Yeah, and then just going back to like getting your arms around what we're doing. A big part of what we're trying to learn in this class, it's not a class on physics. It's a class on doing circuit design. And you need two things for circuit design at this level. You need to have a feel for what different circuits do, what does a diode do, and then you need to use some level of mathematical rigor. It's not very difficult math, we're not doing, differential equations or anything like that, but well, that dog is angry. Yeah, it doesn't like to see other dogs on the street. But sorry guys, but you need to like basically have the KCL equation, KVL equation, etc. And so you need to be somewhat rigorous in doing your math. And the only way you can develop those two, so the mathematical rigor of doing this type of math and having a feel for the circuits, is just do a lot of problems. And there's just no way around it. Just attending the lectures or reading the book, etc., isn't going to get you there. You have to just do a bunch of the homework problems. So the upshot is like start doing those and sort of develop a feel for what it is you're doing at a high level. What is it that you're trying to achieve with this particular problem? All right, so that was my sermon for the day about trying to center us about what we were doing in this class. Do you guys anybody have questions about like a real high level questions of why we're doing what we're doing, or our approach or anything like that? What are you guys confused about at this point?
I don't know if you want to just go over a homework problem, but when I was looking at it, I kind of got stuck on 2.19.
Okay, well, I'll give my best shot. Let's see, where do I have the homework? Let me pop it up. Give me 1 second. Okay, I'm there. So what did you, what, just at a real high level, what did you get stuck in? The whole approach, or was it a particular part?
Yeah, just kind of the approach on how you tackle this, because I know like in your solutions, how you just kind of like threw random, like I think it's IX equal this, and I'm just not sure how you pick those values.
Got it. Okay, okay. Let's try it. Let's do that. Okay. Square paper. Okay. So the problem actually, whoops, looks like something we were looking at in the last lecture. We have a voltage V sub X, and then we have a resistor R1 that's 2 kilo ohms, and the diode D1. And there's a current flowing, right? So there's only one branch in this thing. So if you put a voltage here, you're just going to have one current going through those both. Okay, and is the question, let's see, I'm looking at the solution. So what was the question? Is it that what's V sub, what V sub X does it turn on, or?
It says to calculate VD1 and IX for 4 different voltages of VX.
Got it. Okay, thanks. So VD1, so calculate VD1 and I sub X. Okay, so VD1 is the voltage across this diode, and this is I sub X. And then we're going to do it for V sub X is equal to 0.5 volts, 0.8 volts, 1, and 1.2 volts. So I'll probably just take a couple of these and like play around with them. Okay, and it's giving us a
I sub S was also given.
Yeah.
That's the 2 times 10 to the negative 15.
yeah. So, so this is one of those problems where, unfortunately, like you can't use these models, okay? And so this is mostly to show you guys how painful this can get. I mean, that's like not using these simple models, and that at some points, you have to use a more complex model, okay? So when you have this kind of situation where you're given I sub S and you're looking for actual voltage across the diode, that's an actual voltage, right? Not an estimation. You have to use basically this model for the diode. I is equal to I sub S exponential of VD over VT minus 1. Okay, and again, VT is KT over Q, and it's 25 millivolts at room temperature. 25.9, I always get
I think it's 26.
26, yes, 25.9 millivolts, or 26 millivolts. Okay, so it's basically a constant, because usually we're told to do this at room temperature. Okay, 2.1. Okay, so why do we have to do this? Well, if you look at, like I was kind of saying the other day, if you do the only choice you have to do is to do a KVL around this thing. So basically the Kirchhoff's voltage law says that if you add all the voltages around the loop, it should add up to 0. So basically you get V sub x minus this voltage across this resistor is I sub x R1 minus VD1 is equal to 0. Okay, if you take this voltage, subtract out this voltage, subtract this voltage, come around, by definition, it has to be sort of equal to 0. Can't be any higher. Okay, so moving this stuff around, you end up with V sub x is equal to I sub x R1 plus VD1. Okay, so because of the way this is set up, it's making me rewrite this in terms of VD1. So I'm just going to do that. So this is one equation we'll have to remember. You guys will have to get comfortable with using and remember. And the other one, you either want to remember it or like you memorize it, whichever one you like. But basically, it's basically VD1, we sort of VD in terms of I sub S and I. So first thing is when the diode is on, because we have this because we have a very steep increase in current. Because we have a very steep increase in current, this -1 quickly becomes, when the diode is on, quickly becomes negligible compared to this value. So first thing is we can just kind of get rid of this. Because in this case, look at this thing. As V sub x goes up, as it increases, look at the way the diode is hooked up. So this is the P side, this is the N side. Means that you're turning the diode on as progressively as this voltage increases. You're not turning it more off. So basically I can approximate this as I is approximately I sub s exponential of VD over VT. Okay, so then I can rewrite this by saying VD over VT is equal to natural log of I over I sub s, or VD is equal to VT natural log of I over I sub s. So this is I sub D. Okay, so these are the two equations that you guys are going to have to, they're just the same thing, just sort of rewritten. So, excuse me, I'm going to plug this back into this guy. And so V sub x is I sub x R1 plus V sub t natural log of I. So ID, because this current I sub x is the same current that goes through D. There's no other place for it to go, right? It has to go flow to R1, then flow to D1. So I just use I sub x here for I sub D over I sub s. Okay, so this is the equation we're stuck with, okay, to try to solve. So we have R1. Okay, great. We have V sub t, it's a constant, and we have I sub s. where we have Vx in terms of sort of what is this, a linear function of I sub x and a natural log function of I sub x. And unfortunately, there is no closed form solution for this. I mean, you could try to do some, like, I don't know what you would do, but if you just try to solve this, and you guys are welcome to try, I don't know how the heck you would do that, because it's, you know, one thing is it's sitting in natural log, the other one is linear. So again, no closed form solution for this. And the way we would go about solving this in this class is by doing like a numerical method. Okay, so we're gonna go and take some guesses for, you know, I sub x, v sub x, etc., and see what converges. Because, and let me say one more thing. So that's so let me stop right there. So we're gonna, there's no closed form solution. So the approach we're gonna take is gonna be a numerical one. Okay. So now let's look at how we could even go about doing this. Okay, so let me take you back. There's one thing only that helps us do this. Okay, which is this. So this is like the same as V sub D. So the V sub D, where should I put it? Okay, let me put it this way. Okay. All right, so let's go back to thinking about this diode. So the equation for it is I is equal to I sub D is I sub S exponential of VD over VT minus 1. Or V sub D is VT natural log of I D over I sub S. Okay, so I'm trying to think of how best to explain this, but the one thing that really helps us with the only thing that saves us with this numerical analysis is that a diode that's on, so a diode that's turned on. So let me like take, so this is zoomed in picture. If I do a zoom out picture, which is not really that zoomed out, is, like I said, you get this exponential takes off very, very quickly. If you actually start plugging in numbers for this exponential of EDBT, it looks like just a straight up line. Okay, and then if I plot this I sub S, as you can tell, like here's a typical value for I sub S, 2 times 10 to the minus 15 amps. I don't even know, like if you have, unless you have specialty equipment, you can't even measure such a thing. Just in this, it's just only computationally useful for us. Like if you try to measure it, you'll get 0 basically in any place in Cal Poly and maybe Device Lab, you'll be able to do it. So it kind of looks like this, just zoomed out, okay, in your oscilloscope or whatever. So the good thing about this equation is that a diode that is on, a diode that is on cannot have a huge range of voltages. Okay, so we basically call this voltage VD on. So in our simplified models, this would be VD on. So in our constant voltage model. The reason for that is if you, let's say you somehow you wanted this voltage on your diode, you'd basically, because this is such a fast ramp, you'd need an infinite amount of current to this VD on. You just can't, like it just this, you need to pump so much current. You need to pump, you know, gigaamps of current to get to this level. You just cannot because of this exponential model. Okay, this is such a fast rise that you can't, it's really difficult no matter how much current you try to increase because of this natural log function. As you just jack up this current as much as you want, make it 10 amps, 100 amps, 1,000 amps, this guy is just not going to go up that much just because of the way this natural log function works. Okay. And then if you go much below this VD on, also because of this same thing, because of this natural log function, the diode quickly turns off. So it turns out that in a diode that's on, the range of VD ons in a diode, well, let me just say range of VDs in a diode that is on or is forward biased is really limited. So this is good for us because if you have a limited range of possible VD voltages for an on value, we can kind of throw in a number into our equation for VD on, etc., to start this numerical procedure, and I'll get into that a little bit. And it's not like we can plug in like a 10 volts or 100 volts or minus 100 volts. Those are not the ranges that are possible for a on diode, again, because of this very steep curve. You're either basically an on diode is sort of right around here. And the way these doping concentrations work, again, notice this, even to start with, this is sort of the built-in potential, also has a natural log function of the doping concentration for acceptors, doping concentration for donors. We talked about this a little bit, but at the manufacturing plant, they also don't have, like, they can try to put as much dopants as they want in either one of these. They're not going to get this thing to move very much. So all this stuff means that you have a really narrow range of VDs that are permissible. So let's see what that range is. So there's two possibilities. So for what are called discrete diodes. By discrete means, this is just a term people use in this business, means that these are individual diodes, say. These are what you would have in the lab at Cal Poly, right? You could get like a diode in a package. It's an individual diode. For these, the range of possible sort of VD ons is around 650 to say 850 millivolts. So that's like this range. Okay, it's like a diode that's, I mean, I'm giving you guys something really rough, but if a diode's at, if the VD on a diode is 400 millivolts, it means it's pretty much off because of this. Like you're not going to get a whole lot of current in there. That's gonna, if I plug in 400 millivolts in here, it's not going to give me a lot of current. And we can throw in some numbers later. And if I put in 1 volt in this equation for VD, it's going to give me some huge current. That's like just not possible for the circuit to handle. So this is sort of the range you should expect for on diode. Again, this is just like a lucky thing that allows us to analyze these circuits. And it's part of the reason diodes are used, honestly, because they do peg sort of the voltage. As soon as you turn them on, they'll peg the voltage at that thing, won't let you go any further. So the other thing I want to mention is, like, if you got to remember when we had a diode where we said if it's higher than VD on, this looks like a closed switch. That's why it looks like a closed switch. It just looks like, you know, a closed switch with a battery, and that battery is going to be somewhere in this range. Then
So
go ahead.
if
Sorry.
so I was gonna say, so me kind of understanding now kind of what this problem was to prove is kind of like a lab showing the proof of like the diode's characteristics, kind of why it says, like, in the problem statement, like, note that VD1 changes little for VX greater than 0.8 volts.
Mhm.
So is that kind of like what this is showing, like proving the characteristics of the diode?
It's trying to show you that for sure. It's trying to show you that this method of analysis can be very cumbersome. So it's showing you that you don't want to be doing things this way, because, you know, you'll, like, this numerical method gets like really, really tedious as you're doing this. And but it is a method to use to analyze circuits depending on what you want to do. So it's like really kind of 3 things. One of them is, like you said, to get you comfortable with the way a diode transfer function works and the effects it has on a circuit, and sort of like you said, like a lab, get a feel for it. 2 is to, you know, show you like how you can analyze a circuit like this. And then 3, it's to just show you that like this is difficult to do it, because imagine this is like 1 resistor, 1 diode. If you start plugging in these numbers, I don't know how long it would take you, how many, you know, you start iterating, it takes minutes, right, to get one value out. And we just, again, 1 diode, one resistor. And imagine if it gets more complicated, it gets really, really tedious. Does that help, Brandon?
Yeah.
Okay. Let's see. Does anybody else have a question about this? Do you guys want me to work through this? Or maybe you guys should just try doing the homework and we can try it in a bit. But that's one, I'm sure you guys somebody's got to have questions about this stuff. No? Okay, so let me finish this thought. Sorry, just this is for Brandon, whoever's curious, you might run into this later, but for integrated diodes, and these are diodes that are, so integrated means in a chip with a bunch of other circuits. It's just the way when you're in a discrete device, when you're just building these things, 1Z, 2Z's diodes, and you're selling them to people, you have you have more, you can optimize the diode and you have more degrees of freedom because you only have to optimize that diode. When the diode is integrated in a chip with transistors and other devices, then the manufacturing people have a more limited range of things they can do because they can't optimize the diode and mess up the rest of the transistors. So what happens, what that means is that the VD-ONs in an integrated diode are a little bit higher. They tend to be in the 750 to say 950 millivolts. Okay, range. This is just for your background. But for this class, unless it says otherwise, I think a good number to start with is, you know, somewhere between 700 and 800 millivolts as a starting point, starting guess for your VD value. That's normally where I start. And then start your rate. Any other questions about that, Brandon?
That helps clarify it a little.
Okay. Okay, great. Let's see. Okay. So I'm glad Brandon brought that up. Okay, so that's one way. So this is the circuit, right? So we have you're gonna, as you plug in these different numbers, so you change V sub X. Okay, notice what we're doing. We are stepping through V sub X and coming up with different values of VD1 and I sub X. Okay, so, and like you said, what we do is we have to solve this equation using numerical values. So for each one of these, we kind of like look at it, plug in some numbers, plug in some starting point, and get some values. So now to get a full curve, so let's say we just wanted, again, this is this guy, R1, D1, I sub X. So if I wanted to get a full curve of V sub X, I sub X, I would be, you know, calculating it and a whole bunch of points. You know, this problem is saying you do it at 0.4 volts, at whatever that's 0.8 volts, 1 volt, 1.2 volts. And then we probably have to go, sorry, this is like not written to scale, but probably have to go back and do it at different voltages. And then you'd get some kind of a curve of IX versus VX. Okay, so this is just like a numerical method. And it gives you a really accurate picture of what happens around here. Okay, you'll get actual like numerical values here for, you'll get whatever it is, various currents, right? So, okay, so you get, I don't know, values you get would be, you know, I don't know, 0.18 milliamp and 0.2 milliamp. I'm just making up numbers, okay? So you get that. Now, that's method one, okay? And if, for the sake of discussion, for whatever circuit you wanted to use, or you're using this for, whatever design you were using, for these values were important, you're stuck, you got to do it this way, okay? Now, let's say you're trying to get the same graph, V sub X versus I sub X, but you're gonna do you don't have time. So you want to do a quick and dirty analysis about sort of just roughly what the graph would look like, just to see if this is a good idea to go down this path. Will this circuit even do what you want to do? Because this happens a lot, when you're when you're solving homework problems, somebody tells you specifically solve this problem, you can sit down and work on it. But in the real world, what happens is you have some need for to do some function, you kick around some ideas and you say, oh, maybe this circuit will do it. But then sometimes you're wrong, sometimes you got to modify the circuit, you're just never sure. So it's really cool to have, or not cool, it's absolutely critical to have techniques. Either you have a bunch of sort of like a grab bag of circuits, like a lot of experienced designers, basically they have, like, over the years, they got their favorite circuits, etc. They know what does what, they pull those in, or you have methods of quickly analyzing something. Okay, so now let's say you just want to see if what generally this does with Vx of I sub x, and you want to do it really quickly. Okay, so this was method one of analyzing this. And this is using this exponential model. Okay, so now let's say method two, I want to get a quick estimate of what's going on. And so I am going to use the ideal model now. Okay, so this is what I'm going to do. Exactly the same problem, but I just want to get a quick estimate. So this is what I will do. First, I'll assume that V sub x is very negative. Okay, I'm going to go, okay, well, V sub x, like out here, what does V sub x do? Yes, I'm going to go V sub x very negative, like minus infinity. So there's no question, I'm not going to play around with, what if V sub x is minus 1 volt? I'm just going to say V sub x is like minus 10 million volts or whatever. So just, I'm pretty sure it's doing something. So if this point becomes negative compared to this point, okay, if I just say V sub x is very negative, that means, remember the ideal model, so the exponential model has this, basically by definition, it has this equation that describes it. The ideal model does not have an equation that describes it. It's got this mental model, which is piecewise linear, and it's that if this end of the diode is more positive than this end, then the diode is like a closed switch. And if this end of the diode is more positive than this end, then the diode is an open switch. So there's no continuous equation. We just have two possibilities. Either this side is higher than this side and we use this model, or this side is higher than this, lower than this side, and then use this model. So in the case where this is very negative, basically we end up using this model. So I'm going to redraw the circuit. So I want to replace the diode with an open switch. Okay, so this, because now I have an open switch, there is no current flowing. Okay, no current flowing, so I sub x here is equal to 0. Okay, and then so that's one. This is sort of going to this end of this curve. Now going to this end of this curve, V sub x is very positive, is very high. So this guy goes very high. Then if this guy, again, is plus infinity, right? Very, very high. So there's no question that this side is higher than this side. Then I'm going to replace the diode with a closed switch. So I'm going to force that situation. Okay, so now what happens? Now it's like I just have a resistor tied to the ground with a V sub x across it. So I sub x is equal to V sub x over R1. What was R1 in this case? R1 was 2K ohm. Okay, and at some point, the circuit has to go from this guy being zero current to I sub x being V sub x over R1. So at some point, these two have to kind of equal to each other. Okay, and the only place where they can equal to each other, so V sub x at, minus infinity, and so sorry, so the I sub x's have to be equal to each other. So I sub x is equal to 0 is equal to V sub x over R1. Yeah. Sorry. So I sub x is equal to 0 and in here, and that has to equal, because it's because you can't have a discontinuity. At some point, you got to go from here to here, and you want to know where that is. So these two have to equal to each other, and the only place that that can happen is if V sub x is equal to 0, right? Do you guys have a question about that? That's kind of confusing. Okay, so now I can draw my quick and dirty model, okay, which is V sub x, I sub x. So here, it's I sub x is equal to 0, below 0. And above 0, I sub x is V sub x over R1 over R1. So it just looks like this. And so it's 1 over 2 kilo. Okay, so that is so this method is a quick and dirty method of sort of getting the same curve. It won't tell me what's going on, exactly where my inflection point happens. It won't tell me, sorry guys, my dog's just going to town here. It won't tell me a whole lot of stuff, but it tells me that this is the general shape of my circuit. Okay, so this is generally what the circuit's doing. I hate to do this to my dog, but I have to go draw the drapes so she doesn't see the dogs walking by here. So hang on for a second, guys. I'll be right back. Okay, guys, sorry about that. I brought her in here and closed the door so she can hang out with me and feel more peaceful. Hopefully she won't bark. All right, so so does that make sense, guys? Like how these two methods, you depending on, it's the same circuit and you're just trying to find different things in this circuit. One of them is you're trying to get, and maybe this is a good analogy is, you're trying to get something done. You come up with this circuit as an idea. You do a quick analysis to make sure it is giving you roughly the relationship that you're looking for, or maybe just tells you, again, within a few minutes that you're barking up the tree, if you'll excuse the pun. And, or it'll say, yeah, it's, does what we want roughly. And now to do your detailed design, you start doing an analysis and say, okay, well, where does this inflection point happen? What exactly happens in my circuit? And, a lot of times you don't even, especially with diode circuits, you'd never even have to go much further than this because, you're looking for some basic functionality and this is like good enough. But any questions about that? They're just different models for exactly the same thing. And one of them is going to make sort of analysis a lot simpler.
Is this likely to be something that will be tested on?
Well, the way the tests work and the way the problems work is, I'll tell you, use this model, use the ideal model to solve this, use the ideal model to get me I sub x versus V sub x for this circuit, or use the constant voltage model, or, use the exponential model. So I will tell you guys, this is what you want to use. Was that your question, Brandon?
Kinda. I just wanted to know if a problem like this would show up on or
You mean a problem like 2.19, for example?
yes, correct.
Yeah. It might. Yeah. You don't like 2.119?
I just wanna spend a little bit more time, I suppose, like going over it just so I could understand the process in which we go through a problem like this.
Yeah. Yeah, you unfortunately, like, you have to get somewhat comfortable with this iterative method of coming up with an answer in this type of circuit. And again, it's kind of tedious, but it's just something like you need to get your comfort with it. Any other questions, guys?
Yeah, can you explain why again for the 2.19 problem you got rid of the -1 on the exponential?
Sorry, can you say that again?
Yeah, you got rid of the -1 on the example that you just did from the homework. Can you explain why you did that again?
Sure. So it just comes from the fact that all the VXs that we're talking about, 0.4, whatever, all those guys, means that you're putting in some kind of a plus minus voltage here. You just don't know how much. Okay, it's not going to be minus plus voltage because you got, let's say if you got 0.4 here, you might have some voltage drop across R1, but this guy is going to be more positive than this one. And because of the way this equation works, this exponential function works, as long as you are in this sort of in this positive space, as long as V sub D is positive, this number ends up being like very quickly much bigger than -1. Because this V sub t is around 26 millivolts. So that even, you know, a small, whoops, I wrote this equation wrong. Sorry, guys. There's parentheses. I keep putting the parentheses in the wrong place. Parentheses should be here. If you, like, let's say if you plug in a, well, let's do it together. Let me just try plugging in 50, let's plug in like 50 millivolts there. So it'd be like sort of exponential of 2. So exponential of, so if my V sub D is 50 millivolts, so there'll be like roughly exponential of 2, roughly, right? And that's around 7.3, which is bigger than much, we could say much bigger than 1, right? And if it's now, let's say it's at 100 millivolts. Now at 100 millivolts, we're at about exponential of 3.6 or something, and that's 46, which is now, it's definitely much greater than 1. You know, 46, 45, it's kind of like the same number at this level. So basically, if you have a diode that's on, you basically approximated at just getting rid of that 1. That, if one way to look at that 1 minus 1 is it's kind of making sure that when you go into the negative territory, you end up with minus I sub s, because this you'll as soon as you go into anything below 0, this turns into an exponential of a negative number, which is a very small number. And then, so this becomes much smaller than -1, and you end up with I sub d is equal to minus I sub s for anything below 0.
So that's what you were kind of saying before, where in forward bias, that 1 is negligible. It only really helps map out in the reverse bias portion.
Essentially, yep. Yep. I mean, I'm sure like we'll, you know, if you were gonna logically argue about it, there'd be some pretty specific values of VD and I sub s. Well, no, sorry. Some pretty, like we could solve this problem to see where these two numbers would be kind of, you know, similar to each other or something like that, but it would just be sort of a philosophical discussion. You can really think of it as like on or off. It's like sort of what the diodes are doing. Any other questions, guys? Let's see. What else do I want to talk about? Let me just do one more of these circuits from the lecture notes that sort of brings us to, so far, so sort of brings us back to our earliest discussions. So let's do this. So I think at the beginning here, where we were talking about, you know, a useful diode circuit, and one that's, you know, it's everywhere, which is this thing that's in your power bricks or whatever you want to call it. I don't know what these things are. When one end goes into the wall, the other one has a USB output to charge up your cell phone or whatever. Is, you know, we need to do a rectification function. We need to get rid of part of this AC signal. The AC signal has no DC component, but our cell phone wants a DC voltage to charge up our cell phone battery. Like I just installed, Tesla equipment and battery in my house, and it gets pretty complicated because the battery and the solar power are creating a DC voltage. Just how these things work. Batteries pumping out a DC voltage or needs a DC voltage to charge up, but all the appliances in the house are used to working off the grid, so they're all using AC, this 110 volt AC signal. So that's just the nature of the beast. So the problem is the stuff coming off the wall is completely AC, and we need a DC voltage. And so we said, well, one way to do that, or one of the only ways to do that, is to try to get rid of this part of this negative value. So end up with something with a DC component. And we can think of, this isn't, as we'll see, this isn't the optimal way of doing it. It's more for illustration, but let's say how we can do that, right? So there's an example. Where is that example? So, okay, and that is this circuit, which is just a diode and a resistor. And okay, so far, like for example, in this previous problem, we were trying to plot the current going through, the circuit as a function of the voltage at the input. Here's a problem where we are trying to plot the voltage versus voltage. So we want to look at V out versus V in. So we actually want to do V in, V out. Okay, so well, I've got 2 minutes to do this. I'll do it my best shot. So first you look at, again, V in is minus infinity. Okay, if V in is minus infinity, so this is very negative, it's very positive, this diode is off. So I'm going to redraw it. Always redraw it as my equation. Redraw that schematic. Don't take shortcuts. This is my advice. So in this case, there is no connection between V in and V out. And basically it just looks like V out is 0. There's no voltage. There's no current coming from V in to create a voltage across R1. So V out is just going to be equal to 0. Okay, does everybody see that? I mean, to get a voltage across R1, and V out is, this voltage across R1, you would need some current coming in from V in. And there's no current coming because you have an open switch. Okay, so then for V in being very high, so this point gets very positive compared to that point, meaning I can replace this with a closed switch. Okay, and in this case, you have a current going across R1, but because I have a direct connection between V in and V out is just equal to V in. And then what's the crossover point? Some point you have to cross over one, so that means this has to equal to this. So V out is equal to 0, is equal to V in, which means V in is equal to V out is equal to 0. So all these are easy samples. So if I was going to plot all that, then V in, V out. So when V in is negative, is going negative. V out is just equal to 0. And at this point where V in is equal to V out is equal to 0, things shift over to V out is equal to V in. So it'll be a curve like that. Okay. Now, as the last thing I'm going to say, sorry guys, keep you an extra minute. Let's say, so this is my circuit. This is the transfer function, V in versus V out. Now let's say I gave this a sine wave. Okay. So a sine wave has positive components. So this is time. And this is the voltage, right? So if, so I'm just going to draw it here. So this is the input. So it's going up, coming down, going up, coming down. So this is time. So let's say I want to plot V out. Sorry, time, and then V out. So I'll just do it by inspection here. Every time my input is positive, okay, it's positive over here, my output is just equal to the input. So every time I'm positive, my V out is equal to V in. Okay, so I can just draw it like that. And every time I'm negative, so every time I'm negative, every time I'm below 0, every time I'm below 0, the output is just 0. So the output just looks like 0. And then I become positive here again, and I get this. So this is a circuit. Basically, this circuit is doing what we wanted to do in that charger circuit. So it can take an AC signal, okay, because of the way it functions, it only lets, when it's positive, when the signal is positive, it lets it through. When it's negative, it blocks it. So it does this rectification function. Okay, guys, I'm going to leave it at that for today. Any questions?
Does that say time?
Yeah, sorry, this is all time. Yeah.
This is kind of just like the whole rectifier thing, turning an alternate current to a DC current, right?
Yep. Yep. Any other questions, guys? Okay, have a good weekend.
Thank you. You as well.
Bye.
Thank you, Professor.
Yeah, what's up, Amy?
Thank you.
Oh, okay.
Oh, nothing. Just want to say
Okay.
thank you and have
All
a nice
right.
weekend.
Thanks, you too. Take care. Bye.